no way out for the information, and it's just going to be swallowed up by the black hole. So although Stephen Hawking changed his mind a few years ago and said that information wasn't true after all somehow, I think he was right originally. So I fight with Einstein on saying that Einstein was right to introduce the cosmological constant and wrong to retract it. And I think Stephen was right to introduce information loss and black holes and wrong to retract it. So here we have a picture of the phase. You have to know what phase space is for this, but let me just describe the idea here. In order to define entropy, you see, you really need to know what phase space is. Phase space, you have lots of particles, it's the positions of momentum of all the particles collected together, and you have a huge dimensional space, and you have volumes in that where the microscopic parameters can do anything they like, and the macroscopic parameters which define the situation like temperature and pressure and things like that, chemical composition. And if you lump together all the regions in the phase space, which have the same macroscopic parameters, then you want to volume of that. And that's the B here, and this is Boltzmann's formula for the entropy. And the thing about that is it satisfies its beautiful activity. There's a log there, which is has this additive property. If you are independent systems, then the entropy is added. That's all I'm really using from that. But here you see, what's this picture? Well, here we have the phase space before the black hole has swallowed its information. Here we have a much smaller phase space after it's swallowed it. And usually when you talk about phase space, you think of a curve in the phase space representing the evolution of your system. And there's this thing here, that's the evolution of the system. But when you lose phase space, this whole picture collapses down to a much smaller one. And this evolution continues like that. So that's what I'm saying. When black holes disappear, they don't disappear, they don't disobey the second law of thermodynamics. They sort of transcend it. Because you're moving from, it's like this picture just had a minute ago. So if one of these W and V represents the entropy external to the black hole, and the other represents the entropy which is lost by the black hole, then your original entropy is this one, but then you throw away the part which is lost in the black hole. And it doesn't make any difference to people outside whether they think the second law is violated or not. They think it's not violated. They think it carries along happily. But if you want to count up the degrees of freedom for the whole universe, you have to take into account those which are lost in the black holes. And that's how you get the entropy to be. Put it like this in this picture, the entropy is going up all the time, but every time the black hole disappears, you simply take away a big constant from it. And the next one disappears, another big constant that's taken away. Close up to the Big Bang, there are no black holes left anyway, so you cross over here without much change in the entropy. But it's just the entropy notion gets redefined each time black holes disappear. And that's what enables the second law to be consistent in this picture. It's a slightly subtle issue, and I don't want to go into it anymore here. I want to mention two things. One is observational facts. Can we tell if this theory is right? In other words, can we see through the eon into a prior one, into the eon prior to ours? Can we see through the Big Bang? See, often you think, how could you possibly see through that great hot stuff at the beginning when everything gets churned up? It's not so churned up as you might think, because of this scheme, that photons come straight through. Other things come straight through. So let me indicate the picture here. This surface here is the conjunction between one eon and the next. And of course, I need another few dimensions to make this realistic. I've only got one spatial dimension and one temporal dimension there. You have to imagine that there's three spatial dimensions. In this picture, at least I'm indicating two spatial dimensions. But this is really a three-dimensional surface. It is a join between the previous eon and our eon. This is us looking back. This surface here, it's actually, I'm calling it the crossover tree surface, which would be the Big Bang on our side, and it would be the remote future on the previous side. Actually, what we're seeing is it's just a little bit ahead of this, of what one's looking at. is the surface of last scattering. The microwave background comes from this surface just a little bit in the pictures after the Big Bang. But from what I want to say here, you can think of it as more or less a Big Bang. So we're looking back at the Big Bang, and this is really a big sphere. That's it. The orange sphere which represents the past intersection of our past current. Now here we have the crossover surface looked at the other way. And here we have a couple of black holes in some galactic cluster. Now you see, as the universe does this accelerated expansion, things get more and more separated and they get remote from each other. But clusters of galaxies will essentially, on the whole, remain bound. So they don't partake of this accelerated expansion. They stick together. At least occasionally things might get thrown off and so on. And if the mass decays away, they probably will dissipate eventually. But nevertheless, for a long time they'll hang together, and in these galactic clusters will be galaxies running around each other. Now and again, these galaxies will collide with each other, as seems to be the case when it happened to us, when we run into Andromeda, or Andromeda runs into us. Apparently we're heading for each other. Not for a while yet, so don't worry. It's quite possible, I don't know if anybody's calculated the chances of this, it's quite possible that our black hole and that one in the Andromeda galaxy will encounter each other, get close enough that they capture each other, spiral around each other, and then eventually swallow each other up. And that happens, there'll be a great burst of gravitational wave energy carrying away a considerable fraction of the black hole mass. So you're thinking of the mass energy in two black holes, and a few percent of that will get spewed up through gravitational wave, which is a huge amount of energy, especially if you're thinking of these, say, 10 to the 10 solar mass black holes. So there will be great bursts of energy in the form of gravitational radiation. Now in this picture I've indicated that if you happen to be lucky enough to see one of these bursts, you quite possibly see another one, because these things, you have a galactic cluster which is hangs together. It may be different black holes in different events in the same galactic cluster. It might be the same black hole swallowing others. I suppose that's quite possibly what will happen. It'll get bigger and bigger and bigger, and then it will swallow other black holes in the cluster. And you might expect several bursts like this. Now, what do you see? Well, these bursts will be, again, spheres, as I mentioned. These things will be spheres, and in this true surface you have the intersections between the sphere which we see and the sphere which is the burst. And those spheres intersect in circles. So what you would see would be circles. And because of this repeating of these events, you will see concentric circles. So the prediction here, according to the scheme, this burst of energy will basically give a kick to the initial material. You have to understand how gravitational waves work in this scheme, and I don't think I'm going into details of that here. But they would give a kick to the initial material, and that kick would be something visible to us. Now, I've been worrying about this for quite some time, and not getting people to look for it. About nearly 4 years ago, or 3.5 years ago, I got some people in Princeton to have a look at this. It was nearly 4 years ago. And they had a go, and I thought there was some evidence that they were seeing something, but it was pretty inconclusive. Much more recently, 3 months ago, I got in touch with this Armenian colleague, Bahir Gozadyan, for some other reason. Well, I was hoping that he might be able to disentangle distorting effects in our eon, and maybe that was the reason we were having trouble seeing the surface. And he then had a different way of looking for the surface. And his method was not to look at what I was thinking of as the thing to look for originally, which was to expect that you might find a temperature which was slightly higher or slightly lower than the average. Why do I say slightly higher or slightly lower? Well, it depends upon whether the burst of radiation is coming towards us or going away from us. And one or the other would give you a warmer, slightly warmer circle, the other would give you a slightly cooler circle. But it's a slightly complicated issue. And he thought a simpler way of thinking about this would be not to look at the average temperature, although he does that too, but to look at the variation in the temperature over the whole circle. So what he was saying is if you take a proposed circle to one of these events, and you look at the temperature in the sky, and is the average temperature over that region a bit more uniform than it should be? And that was what he claimed to see. And I saw him in October last year, and he said he got some interesting graphs, just preliminary, and that he'd been mapping them. The people in Princeton had looked at a fixed radius in the sky and trying to see whether there were randomness in the whole measure of the whole sky. That turned out not to be the best way of doing it. His way, John's way, was to look at individual centers in the sky and then looking at different radii for a given center. And he said that he seemed to see cases where the variance in the temperature here, say, I've done it in pink sort of deliberately because they're rather hard to see. So you may find it hard to see, well, that's perfect. So here we have one of these rings where he was claiming that you would see an anomalously low variation in the temperature. And so I said, oh, you've done it that way, have you? Then if you see one of those, you ought to see several with the same sentence. And he looked at me and said, well, that's exactly what I see. And so he showed me his graphs and so on. Well, this is I'm going to cut a fairly long story a little bit short, because he did write a paper which we put on the archives, and it encountered an awful lot of opposition. As you might have expected, because this is saying that, okay, inflation isn't the right explanation, there's something else going on, and that's pretty unpopular. But also a lot of people were saying that he'd done his statistics wrong, and that what he was claiming to be an unusual event was not that unusual. And I will say a little bit more about that, because there are several groups who are saying this. I want to show you two things. One thing is this, which is just a particular example. One way of addressing the people who complain that we've done the statistics wrong is say, all right, let's do it your way, and see if we can find a few examples which even so are so unlikely that they're pretty hard to assume that could come about by chance. And this is one example. There are several others like this, but this is one example. What do these dips mean? Well, you see this is the variation around the ring, the variation in temperature. So if you see a dip, that means it's very uniform. So this dip is possibly one of the rings. As you go this way, you're looking at rings of greater and greater radius. So this would be one example, which maybe you could see, the sort of using other people's statistics and looking at this example, the chance of seeing one of these over the whole range of 1,100 points, and you've been looking at the centers in the sky, you might expect to see one of them, but now we see two of them. So that seems to me rather extraordinary. And I think the chances of seeing that, even using the rather more stringent criteria that other people are using, it seems very unlikely that you would see events like this without them actually being real. So the claim is that this is a real event. In fact, he has an example where there are 7 of these things. And that's pretty hard to explain in these just being random. I should try to explain what it is. The crucial point in the argument is how do you know how unlikely it is to see a dip this such? So what people tend to do is they simulate the sky. They agree, okay, you see those in the actual data. And this is primarily the thing called WMAP. There's now a better one, which is the plant data, but we haven't got, we're not allowed to see those yet. They're not generally released. But the WMAP is generally released, and so anybody can look to see whether these dips are really there. And yes, they are there. But the question is that something which could have come about purely by chance, or are we looking at something that's really there? And how do you know how likely these things are? Well, what you do is you make a simulation of the sky, which isn't the real sky, and then you find dips that are the speed of the simulation. And the way Penrose did it was more or less take a random sky, a little more subtle than that, but more or less that, and you see, no, it's very unlikely to see these. These you would see 1 in 10 or something. Unlikely to see a dip like that. Or 1 in 10 to 5.